conducting sphere. When we turn the generator on, the generator's sphere becomes strongly positive in charge, and the other becomes strongly negative. We sprinkle bits of fur into the air around the spheres. A very distinct, stable pattern appears. This pattern indicates an electric field. Notice that the field is not quite symmetrical. This is caused by the presence of other conductors, such as people, in the vicinity of the spheres.
Okay, that was just a video I wanted you to watch regarding electric field lines. I think what I'll do is I'll probably email you the other videos. So you all have to make a video for Friday. And I want to spend a little more time talking about the lab. Let me maximize this window. Do you have any questions regarding what's due on Friday? Or concerns? But I've had a couple of questions already. I just want to make sure you're all clear. You're going to make a video which demonstrate that you built the electrophorus and you built the electroscope. So I want to go to the website that has the electroscope. And it doesn't have to be this exact website. You can use something else. But here's a picture of the electroscope. And it's pretty simple. You use a jar. It could be plastic. Yeah, I can do that. I can talk about the lab and what I want to see in the videos. So for the electroscope, you want to build this device, but so it doesn't have to be a glass jar. It can be a plastic jar, but plastic gets charged more easily. So that will affect your results. Probably better to use a glass jar if you can get one. And if you don't have a plastic lid on the jar, you can always replace it with some kind of cover made out of cardboard, just an insulating material. It doesn't have to be a screw-on lid. Okay, it can be a variation of what you see in the link I gave you, and there's other sites you can search for that talk about how to build one of these. They're pretty simple. Okay, you just need a jar, some aluminum foil. Okay, and you need something like that ball. In fact, and then the instructions in this particular case, they're very simple. You need to make an aluminum ball. I mean, one of the ways is to wrap a spherical object, wrap aluminum foil around a spherical object, or you can just crumple a piece of aluminum. Okay. So the instructions are pretty straightforward. Okay. And so one of the things, what's nice about this lab is you actually get to build something. So what you want to do is, you want to create a video. It doesn't have to be one video. It can be 2 separate videos. You will upload it on Canvas. So let me go to Canvas. And let's go to our class. Let's see. And I'm going to go to the student view. It takes me there soon. All right, so then I can scroll down from your home page, and I can look at properties of charge. And There's a video there that I want you to watch. I hope you watch it or we'll see it soon. This is the property to charge lab that you see. And then there's a discussion book for building the electroscope. And then this is the video. So if I click on here for the video of the electrophorus and electroscope, I go here and then I click submit assignment. And I upload my video. It could be, the video can be one file or two files. I mean, however you want to do it. I don't expect you guys to be experts at editing videos. The screen share is blurry, and that's because of the internet connection. I apologize. The actual video that I'm recording is quite clear on my computer, but the problem I'm having is, in fact, I'm not even doing screen share. What I'm doing is using the software for my camera. So I think the problem is and the font's small too. The problem is the internet connection. So I apologize for that. So anyway, you want to upload it where it says submit assignment. You've all probably done this before. Okay, I'll use the student view. Okay, and I just want a video where I can see that the electrophorus is working and the electroscope is working. So what does that mean? So how do I demonstrate to somebody that the electrophorus is working? So you built this device. One of the things you can do is you charge it. So you can take a piece of saran wrap and just lay it out on the flat surface. Then take the fur, rub it on the flat surface, rub it vigorously, so it gets charged. So you have charged saran wrap. Then you take the electrophorus and place it on top of the saran wrap. With one hand on a water faucet, that'll be your ground, and then with your other hand, with your finger, touch the metal portion of the electrophorus, just briefly. Then pick up the electrophorus and hover it over small bits of paper. It should move. The paper should move. If the electrophorus is charged, you will see a force of attraction between the electrophorus and the little bits of paper. You know, and how long is that? It's probably about 15 seconds of video. Then for the electroscope, you show the electroscope in your video. You bring your charged rod. It doesn't have to be a charged rod, something charged. It could be a comb that you charge by rubbing it in your hair, and bring it next to, without touching the electroscope, and the leaves should move. Yeah, so I not only want to see that you built it, I want to see that it works. Okay,
do you want us to show it working in all those ways you just described, or is just one okay?
Just one of the ways. Just one simple demo that shows that what you built, each device works. That's it.
Okay.
Okay. So maybe you can make 2 videos that are 15 seconds each. Oh, and I want to see your face in the video. Okay. I need to see you in the video too. And basically, if you do that, you show yourself actually doing it, because you can film yourself with a camera. So you show yourself actually going through the process of showing me how it works. That should be a 20 out of 20. Okay.
And also, I have one more question. So the 2 videos are due by Friday. On the to-do list on Canvas, on the 210L Canvas page, it says we have the charge, which is worth 40 points due on Monday, but when I was looking in the actual modules, it shows like the video lab report due the 18th, so I just wanted to clarify what's actually due on Monday.
Well, there's 2 video labs. Oh, did I say before? Hold on, let me go back. Oops. Sorry. So there's two videos that you have to do. One that's on how it's built. That's due September 4th. Okay, that's the video I want you to turn in on Friday. The second video is a video where you go through the entire lab and explain, so you demonstrate the items that are in the lab and you explain them. So there's two parts to this lab.
And that's
One
what's
is,
due on Monday.
I'm sorry?
But then that's what's due on Monday, the actual explanation video.
You say Monday. Where does it say Monday?
When you on Canvas, when you go to the grade book, or I think it's the grade book. Yeah, September 7th. It just says charge, and it's worth 40 points.
Oh, hold on a second.
Maybe I don't know if that's the right date or if I'm just not thinking of that thing.
Oh. There's two sets. I forgot to erase the bottom one. Sorry. I got to erase the bottom one. Everything where the second set, ignore that.
So there's nothing due Monday. Okay.
Can you see my screen? I know it's kind of small.
It's a little blurry, but I can see better now. Yeah.
Okay. So it's this one I'm highlighting is due on Friday.
Yeah, the video showing that we've built the electroscope and the electrophorus and that they work.
This is that you see here.
Uh-huh.
It's something I forgot to erase. I apologize.
Oh, okay. So I'll just ignore that. All right.
Okay, just ignore this. I didn't realize that. I thought I got rid of all that stuff. So I forgot. This one should be erased. Okay, that whole section below.
Bring that up.
So let me do that right now.
And yeah, just so you know, on our screens, they're randomly placed throughout the grade book because of the due dates. So.
Okay. You refresh your screen now. Look at it.
Yeah, it's on.
Okay, good. Sorry about that. I copied this from last semester and I forgot to get rid of those.
Okay, cool. That makes me feel better. I wasn't sure what to do there, so.
Okay. Yeah, so what's due Friday is that first one. It's this video of built electrophorus and electroscope. That's it. And then on the 18th, the actual lab itself. So I want to go through the lab real quick. So I had a question on this. I wanted to go over it. So let me find my file here. I'm sorry, I'm juggling through two windows. So. I'm sorry, not two windows, but two screens. There we go. Okay, so there's three parts to this lab, and when you get the lab kits, you'll see the material in lab kits. So we provided the balloons for you. We provided the fur, the silk, and the wool. You will provide the jar and the can. So if you notice the superscripts or the footnotes here, number 2 says must be provided by the student. Okay. So the salt and the sugar, we're not going to put that in the kit. Okay, and the saran wrap, we're not putting that in the kit. Okay.
Did you say in our lab the jar can be plastic too, or just the lid? The jars be glass?
It can be plastic, but I think plastic tends to get charged up more easily. So it's probably better to use glass.
Okay. All right.
If you have trouble with the plastic, then I would switch to glass. It'll work better.
All right.
So these are the materials you'll need for this lab. And I think I made a mistake. We did not provide the transparency sheet. That's a mistake. Sorry about that. If you have saran wrap, you can use saran wrap instead of a transparency sheet. So part 1, you have a balloon in your kit, inflated, rub it on your head. and place it on the wall near you. You want to explain what happens. So there's several things that it has you demonstrate. And in the video, in the video, you might not be able to demonstrate all three. If you demonstrate 2 out of the 3, that's fine. They're all based on the same idea. So if you can demonstrate 2 out of the 3 instead of all 3 in your video and explain them, that's fine. Does that make sense? So in your video, you want to actually demonstrate the maybe a couple of these and explain why that's happening. You can draw on the board or whatever you want to do. If you draw pictures on the board, that'd be great. For part 2, it is mainly having to do with the electroscope and how it works. Again, the electroscope is a device that qualitatively tells you if something's charged or how much charge something has as compared to another. Because the more charge an object has, the more the aluminum foil will move when you bring the charged object near it. Now, ideally, when you make an electroscope, you want gold foil, but we don't all have gold foil. We'll use aluminum foil. So make sure when you build the electroscope that you use the thin aluminum foil, not the heavy one. And so, again, you're going to go through, again, you don't have to demonstrate every single item. Just explain most of them and then talk about why the effect happened. Okay. If it's something that you can't show in the video, then you don't need to show it, but maybe you can talk about it. Does that all make sense? I'm really looking at do you understand the material? That's what I'm looking at. And part 3 is the electrophorus, straightforward. Okay. There's several parts to it. I mean, when you do the video that's due Friday, you will have already, it's basically half of these steps. Okay. But there's some interesting questions that you should experiment with. Can you use the electrophorus over and over again without recharging it? That's a question. How's it getting charged? Well, those are the kind of questions you want to answer. So your video is just going to basically be show me a phenomenon that's in the lab and explain it. Explain why. Now, when you explain why, you want to explain it in terms of concepts that I talked about in class. Polarization of charge, formation of dipoles, all that kind of good stuff. Okay, I want to see you being able to integrate what we discussed last week. Questions? Concerns? Anything not clear? Silence means you have no questions. I just want to make sure if you have questions, please ask. And like I said before, once Tyler is done with distributing the lab kits, then he'll probably set up some hours where he can answer your questions too. Okay, so in the meantime, I want to say a few more things about, actually I want to say some things about dipoles. And I know some of the materials later on in chapter 25, but I want to talk about it here. I'm not going to go into the material in chapter 25 right now, but I'm going to talk about some interesting ideas involving dipoles. Give me a second. So I actually want to begin with an interesting example let me just check this question. No, the video doesn't have to be edited together. If you want to edit it together, go for it. I don't expect you to be an expert in video editing. If you look at the video of one of the problems I put up on YouTube yesterday, you can see that I'm bad at editing videos. Part of it's because I don't have time to do a good job at it, and I understand that. So you don't have to edit them together. And if they are, they don't have to be perfect either. Okay, just they can be 2 files. That's fine. All right, Spencer? Okay. So one of the applications of properties of charge is the Xerox machine. And you all can see that Xerox machine clearly, right? Okay.
Yeah.
So it is a complicated device. I'm only going to focus on a Xerox machine, a copy machine, that makes black and white prints. So if you notice in that picture, you see an electrostatic drum. This electrostatic drum has a coating on it. It's a photoconductive coating made out of typically selenium, which means that when you shine light on it, it will conduct electricity. So the selenium is negatively charged. Okay, so the coating is negatively charged. But if you shine light on it, that negative charge goes into the drum because the charge will conduct into the drum. Okay, so now at the top of the page, at the top you see a document that's going to be copied. You put the document there, and then a light shines on the document. So you have a bright light. Of course, the document has dark spots where there's ink, and then there's light spots where there's no ink. So in the locations where there's dark spots, the light will not shine through onto the drum. In lights where there's, in parts of the copy of the document where there is nothing printed on it, the light will go through and shine on the coating, allowing it to conduct. So what happens is, when you shine the light through, you will have the parts of the document where there is no light on it, where there is no ink on it. You'll see the light go through onto the drum will conduct, and the negative charge will go into the drum. But on the locations of the document where there is an image, for example, the light will not go through. That's going to keep the drum charged. So now you send paper through. Okay. Actually, I'm sorry. You send toner through, and then the toner, which is positively charged, gets attracted to the negatively charged areas on the selenium. Now you send the paper through, which has a negative charge, and the negative charge on it is even higher than that of the selenium. So that's going to pull up the toner towards the paper. So the toner will get attracted to the paper that's coming through. And I'm talking about this one right here. It goes through over the drum. The toner will get attracted to the paper, and then the paper goes through and it gets heated so that the toner gets heated, and it goes through rollers so that the toner gets pressed into the paper, and then you get your image, and it comes out the other side. So the Xerox machine is basically using properties of charge, what we're learning here, for it to work. Obviously, there's some more engineering issues you have to deal with in making this work, but that's a simple-minded way of looking at how this device works. Now, if you're talking about color printer, there's actually 4 different systems in it. One's black, and then the other are three colors. And this is designed. The system is designed to combine the colors properly to give you a color copy. Any questions? Okay. So remember when we talked about charging objects, when we induce a charge on a uncharged material, or not a dipole, we induce a dipole on a uncharged material, you get an asymmetric distribution of positive and negative charge within the material. So, for example, when I did the demonstration with the 2x4, and I brought the charge rod near it, when I brought the charge rod near the 2x4, the positive and negative charges within the 2x4 separated so that the unlike charges is closer to the charged rod and the like charge stays further away from the rod, and that causes a force of attraction. That separation of charge produces a dipole. Remember, the dipole is defined by the letter P, or is denoted by the letter P, and it is a vector that is directed from the negative charge to the positive charge. The vector is Q times L. And remember that the plus and minus charge each have the same value. So the Q is the charge, the total charge in either one, the positive or the negative. Okay. The P is Q times L. And so I want to say some things about the dipole. Remember that molecules in which the centers of charge do not coincide are called polar. Basically, they have a permanent electric dipole moment. An example is water. The water molecule is a polar molecule, and there's others. Those of you who've had chemistry probably can remember a whole bunch of various polar molecules. Molecules in which the center of charge do coincide are called nonpolar. Of course, you can always induce a dipole moment in such materials, like I did with the with the 2x4 last week. The dipole is important in studying physical systems. That's why I'm spending a little bit of time going over this. The dipole can be used to understand effects of electric fields on insulators, like as we've been discussing. It can help us to understand microwave ovens, radiation from atoms, radiation from antenna systems, and it helps us to understand collisions between neutral atoms. And a lot of times the dipole is used in an approximation, as an approximation to a very complicated problem. A lot of times when you're solving problems involving electromagnetic radiation, you have to do an integral. The integral is very complicated. But you can expand the function within the integral a lot of times in a power series. So you'll have a something first order next, then something second order next, etc. And you've done this in Calc 2. And when you expand in a power series, there are many cases where only the first term is kept and the rest of the terms are going to be too small and we can ignore them. That first term has a form that looks like you have a dipole moment in it. And so we call it the dipole approximation. So when you talk about radiation from atoms, you're using something called a dipole approximation to talk about the radiation from an atom. And in fact, if you look at the shape of atoms from a chemistry book, you'll see that they look like a peanut shape, which is basically the dipole. the light emitted from a dipole. Okay. This is one of the several systems that are used a lot to make approximations in physics, because there's a lot of physics problems that are hard to solve. When you take 215, when you talk about the mass and the spring problem, called harmonic, and basically it falls under the category of harmonic motion. The harmonic oscillator is used to approximate a lot of systems because the math is simple. Okay, so this is another one, and that's why I'm spending a little bit of time talking about dipoles. So I want to consider the force. Let me change here. Views. I want to consider the force on an electric dipole in a uniform electric field. What do I mean by uniform? It has the same value in every region of space for which the field is defined. Just like when we're doing problems with gravity. Okay, we make G constant, same thing. So I want to consider the force on a dipole in a uniform electric field. So let's pretend we have an electric field that points to the right. And I have a dipole. I'll make this positive and this negative. P is Q times L. A little thing, sorry. I want to know the total force on this thing. These two are tied together, so I can almost think of this as a dumbbell. Okay, so two objects connected together by a really light rod. Okay, I can think of it that way. So if I want to find the net force on this thing, I draw a free body diagram. Remember that the force on a charge in an electric field is given by Q times Z. And since this charge is negative, the electric field points to the right, the force on it has to point to the left. This charge is positive. The field at this location is the same as the field at this location because the field is uniform. Since Q is positive, then Q times Z is going to be the same direction. These two forces are equal and opposite. So when I sum the forces in the x direction, I get 0. So the net force on an electric dipole in a uniform field is 0. But the torque on it is not 0. Same thing, I mean, I could give you an analogous system. Suppose I have a square plate that's pinned at the center, and I apply a force in this direction and a force in the opposite direction on opposite corners of the plate. It's true that the sum of the forces equals 0 on this plate, but both of these forces cause this plate to rotate clockwise. So it's not an equilibrium. Well, the same thing is true for this dipole. If I have a dipole oriented at some angle theta, with respect to the electric field, it's going to want to align itself in the direction of the electric field. So theta is actually going to want to decrease. So there's a torque on this thing. And we can use the concept of torque that was learned in the previous course. Remember, torque is R cross F. Our F is going to be Q times Z. I'm going to calculate the torques about the center of mass. I'm going to call this vector L over 2. So my r vector here is L over 2, and then this vector is minus L over 2 because it points in the opposite direction. So my total torque then is going to be L over 2 cross QE plus minus L over 2 cross negative Q E. The two minus signs cancel. And these two add together, so I get L, cross Q times Z. This is a constant, and Q that I put here is the magnitude of the charge. Okay. I can take this and put it over here. And what's Q times L? Q times L is P. So that's the equation for the torque on a dipole in a uniform field. You might be asking, well, what if the field is non-uniform? Let's not worry about that. Okay, it's somewhat complicated. So what happens? Well, let's say this is a dipole. Let me draw it like this. This is your dipole. When you put it in the electric field that points that way, the dipole is going to want to align itself. Really what it's going to do is it's going to oscillate about the equilibrium position. The horizontal position, the direction of the electric field, basically is considered the equilibrium position. So it's going to do this. It's going to oscillate about the equilibrium position. Okay. Now, because the electric field really is conservative in nature, and something we'll talk about in chapter 25, we can define the energy stored in the dipole. Now, I have to go back, or you have to go back, and look at an equation that's in the chapter on rotational dynamics of our textbook, chapter 10. And in chapter 10, there's an expression for calculating the work done by a torque. The work done by a torque, if you look in chapter 10, is given in the following manner. The magnitude, remember what's the magnitude of a torque? What's the magnitude of a cross product? It's the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. That's the magnitude of the cross product. And so over here then, I would put the magnitude of P times the magnitude of E times the sine of theta d theta. Now, a lot of times, if it's understood that we're talking about magnitudes, I can get rid of the arrow over the letter and these guys. And that's what I did in my notes. So if you look at my notes, those represent magnitudes. Now the problem here, one of the problems here is that my d theta is decreasing. My d theta is decreasing, not increasing. Normally when we do these kind of calculations, we assume d theta is increasing. But it's actually getting smaller. So d theta is less than 0. And so I actually have to put a minus sign there because of the fact that d theta is 0. So this is going to be the work that's done by the torque on the dipole as it rotates through an angle d theta. If I want to do a more finite angle, I would integrate that from the initial angle to the final angle. Now, you also learned that dW is minus du in the cases where we can define a potential energy. So that means du is going to be minus dW going to be P times E times sine of theta, E theta. So if I want to find delta U, I'm going to integrate this. From some initial angle, some final angle. And that's going to give me my change in potential energy. Delta U, U final minus U initial. Now when I integrate sine of theta, I get minus the cosine of theta. So I'm going to get the following. And I define theta initial equals 90 and theta final is just some angle theta, we have to define where our zero is. Generally what we do is define our zero when theta is 90. That makes this 0. And you get that expression for the potential energy. This can be written as a dot product. And so that's the expression for the energy stored. A dipole in a uniform magnetic. Remember that the field is uniform. Just 1 second. Okay. Questions? And I just got to note that my internet connection is unstable. So I apologize for that. Question. What is the net torque? And in fact, let me change the screen so you can see it better. What is the net torque on electric dipoles that are induced in a nonpolar material when it is placed in a uniform electric field? Now think about it. If at one instant in time there is no dipole, and then you introduce an electric field next to the material, isn't the induced dipole going to be automatically in the direction of the electric field? Yeah, I'm sorry, Asher. I'm having internet problems. my video when I upload on YouTube will be fine. But anyway, isn't the dipole that's formed automatically in the direction of the electric field? And if that's the case, then the torque on that dipole is going to be 0. So when you have a nonpolar material and you put it in an electric field, the induced dipole will be already directed in the direction of the field, so there'll be no torque on it. Now the next question is, what is the net force on the electric dipole that is placed in a uniform field? That requires a little bit of work. So I want to actually do a derivation. And I'm going to do a simple case because the general case takes a lot of work. Okay? I mean, I can do it, it takes a lot of work. So let's pretend I have a dipole in a non-uniform electric field. To make the math easy, let's assume that the dipole is horizontal already, and the electric field is horizontal, but it's not uniform. So here's my electric field, horizontal. Actually, it's not uniform though, so I shouldn't draw that right. That's a bad picture, sorry. I won't draw the field because it's hard to draw one. It's not uniform. But let's put the minus charge here. The plus charge on the right. So the x direction is horizontal. And let's say that the field in x direction. Now, this distance is L, the magnitude of the vector that goes from the minus charge to the plus charge. And a lot of times, instead of calling, in these kind of problems, instead of calling it L, I'm going to say it's equal to delta x, just for thought. Because really, in a dipole, that separation is tiny. Now, if the field is not uniform, let's pretend it's well behaved. You don't get any weird discontinuity in the fields. Then the field here and the field here are different. This is the field at x. This is the field at some other value. So the field at x, I'm going to say this is the field at location x. The field here, I'm going to say, is E at x plus delta x. The field at this location is different from the field at that location. As we said, it's non-uniform. And if you draw a free body diagram, the force here is going to be, the force on the negative charge will point to the left, and its value is going to be Q times E of x. The force on the positive charge on the right is going to be Q times E at x plus delta x. In fact, this is negative. So suppose I add them together, right? That's the next thing I do. I draw my free body diagram. I now have to sum the forces. And when I sum the forces in the x direction, I'm going to have this force minus that force. And I can pull out the Q. And just for fun, I'm going to multiply the numerator and denominator by delta x. So that's my expression for the force. But you know, delta x, delta x is small. Delta x is small. I hope you can see that equation okay. And generally, we can make it really small. We can take the limit as delta x goes to 0. What happens to this expression when we take the limit as delta x goes to 0? By the way, isn't it true that this is the definition of the dipole moment? So maybe, let me put the dipole moment here. Let me rewrite it. I want you to look at this term. What happens as delta x goes to 0? What does this thing become as delta x goes to 0? Yeah, I apologize for the bad internet. I don't know. The video will be better. It turns out that this is the difference quotient. If you take the limit as delta x goes to 0, this is a derivative. And that's the force on a dipole in a non-uniform field. For the specific case where the dipole is already along the x direction and the electric field is along the x direction. Now, if this was oriented at some angle, then we'd have to work with components. It becomes more complicated. We can do it, I'd have to do this many times, the same process many times over and over again, but you get a complicated expression. Okay? All right. So I just want to say a couple more things, and then I'll be done. So I just want to talk about an experiment that indirectly verified Newton's second law. It's called Rutherford's Experiment, and Rutherford did this experiment because he was trying to study the structure of the atom. This was before Niels Bohr, before we had any understanding really of what the atom was like. So he basically did an experiment where he scattered X-rays, not X-rays, I'm sorry, alpha rays, which are basically helium atoms with 2 electrons removed, off of gold. So he did this experiment, and his goal was to study atomic charge distribution. At the time, there was a model by J.J. Thomson that described the atom as basically electrons embedded in a fluid of positive charge. It was called a plum pudding model. And so Rutherford wanted to test this. So he scattered X-rays off of gold foil. Basically, he was scattered, not X-rays, I'm sorry, alpha rays off of gold atoms. And he expected some sort, maybe a uniform charge distribution because of the model of the atom. But instead, what he was able to determine was that there was a lot of alpha rays that were scattered in the backward direction. and the scattered particles are scattered in a smaller volume. I'm sorry, let me rephrase that. The scattered alpha rays is not spread uniformly over a sphere, but it has a particular orientation. So Rutherford then said, well, maybe the positive charge in the atom is not really spread out over a sphere, but is concentrated in a smaller volume, which you call the nucleus. So then he proceeded to do a calculation where he assumed that the atom consisted of a center of positive charge, and he applied Coulomb's law. The results of his calculation agreed with his experiment. Thus, one, he showed that the atom consisted of a center of positive charge called the nucleus. Okay. And two, he indirectly verified Coulomb's law. By the way, Rutherford was a physicist who I think it was 10 of his students won Nobel Prizes, including him. Okay. You guys have any questions? Again, I apologize. My internet's messed up today, so the Zoom is not good. But the video I'm filming with my stuff at home will be fine, and I'll post this on YouTube probably after I have 2 more classes today. Probably after my classes, I'll post this on YouTube. Any questions? Concerns? Okay, so I'm going to end it here. Again, I apologize for the bad video on Zoom. I will see some of you in 2:10R.